Okay, so we've seen several approaches to the study of cognition. Pardon me. We've seen we spent some time in the physical symbol system, the idea of high level minds that need to have very structured rules for how they can transform and move information around. We've also looked a little bit lower level and seen the neural modeling approach, where we say, okay, given a single neuron and how well we can model that, what can we build out of it? And then, most recently, we looked at the dynamical systems theory, which involves the idea of, hey, whatever's going on in the mind, whatever's going on with neurons and maybe higher order functions, we still need to better understand the context in which the mind works, right? So that brings us to a broader question and sort of a more sort of a synthesis of some of the things we've been talking about, to say, how is a mind laid out? So, like I said, we talked about how we have different information processing components that work, right? The basic idea that we can set up systems that move information around in all these interesting and neat ways. But one of the bigger questions is, okay, cool, I can show how a neuron could be capable of joining a network of neurons to produce some wild image matching stuff, right? Remember our our good friends the birds, and pattern matching their beaks. But where does that live in the brain, in the mind, in the overall system? And what does it connect to? How do we reach the point where we have a system that takes in five senses, processes it somehow in a very complex, convoluted way, and then outputs things like this sentence that I'm saying, the thoughts that you're having, right? The words you will write and the things that you will achieve today, right? So this brings us to the idea of an architecture of mind. So the big question for mind architects, not really named that, but it's a general field, a general approach. How do we lay it all out? How do we piece together an entire mind out of all these information processing bits? So how is the mind organized? What processing is happening where? What passes information on to somewhere else? And when does that happen? So let's talk about agents. An agent is anything that produces behavior on its own by perceiving and affecting, i.e., creating action. This includes AI systems, like we've seen, certain cognitive modeling approaches where you create a system that's constrained to behave like a human cognitive system, or a dog, or you, or even elevators are agents. Last time you were in an elevator, you gave it input and it produced output, but it also has to know where it's going to be, between floors. What floor does it wait on, right? It has a system programmed into it that decides that. So it perceives the world through button pushes, and it affects the world through its motion. And obviously, these all fall on a continuum of complexity. So let's talk about three different levels of complexity. Now, it's a very much a continuous scale, right? The more complex something is, the more complex the agent. But we'll talk about a few different architectures of some agents. So we'll talk about simple reflex agents, goal-based agents, and learning-based agents. So the idea for modeling all of these and sketching out their architecture is to identify how a system would need to be designed to achieve the level of complexity that we're talking about. So let's talk about a simple reflex agent to start. This is the simplest sort of agent. Very, very dumb life. It has a couple of production rules. If something happens, some state is happening, then create an action. Okay. It has nothing else going on. It just receives information and spits something out. There's no processing or transformation going on. And this is how we might lay out that system. So, environment's on the right and the agent itself is on the left. Something comes in from the environment in terms of percepts, and it hits the sensors of the agent, whatever that might be. And the agent has this question: what is the world like? It relies on the sensors to answer that. Then it consults this condition action rule set, the production rules, to say, okay, if the world is in this state, I will do this action. If the world is in a different state, I will do a different action. If the world is in yet a different state, I might just do nothing. So then whatever action is going to be decided hits the actuators and moves back to the environment. We do something in the world. This might be familiar. We've talked before about the knee reflex, the knee jerk reflex. This is a simple input to one little piece of your body. We could call this little routine a simple reflex agent. It takes an amount of pressure. If the pressure is not very much, nothing will happen. If the pressure crosses a certain threshold, then kick my foot in correspondence to, how hard I was knocked upon, right? So that's funny. It's a sub-agent of our system, but it's a very simple, what we could call an agent on its own. So what's happening? Perception goes in and action comes out. And there's just the one decision. What am I prescribed to do? The knee jerk is, how hard did the mallet hit me? How hard should I kick? Or not at all if it's under a certain threshold. Okay, so that's simple agents. They are very routine, they are very reflexive, and they are very they're dumb, but they're still behaving in the world. A lot of insects are pretty close to this. I mean, they're certainly more complex, but there's a certain amount of planning with some of them, but some are just that simple. They just have a few rules they use to get by, and they manage to eat and survive and procreate, based only on that. So, okay. Now let's talk about an agent that is capable of maintaining goals in mind, not just having simple reflexes, but guiding its behavior by some internal information. So, goal-based agents. They receive information. They try to predict which possible actions can get it closest to some goal, and it will weigh those options. It has some kind of heuristic search or prediction that it's making, simulation, deduction of logic, whatever it might be. It has a way of comparing different opportunities, different options. This has a lot to do with that same kind of heuristic search we talked about in the past, right? How can I search the state space for my ideal options? And then it will choose the best behavior it can figure out. So let's look at that agent's architecture. Here's a goal-based agent. It has the environment, has its sensors just like before, and it has this question of, what is the world like now? But it also has an internal state that it's what's my goal? So that might combine or might change how I interpret what the world is like. So taking my internal state and the report from my sensors, I moved on to what might it be like if I do action A. So this involves other information that is stored internally to the model on the left there. How does the world evolve? How do things play out in the world? A lot of it is physics, but also, if I move this thing, what does that mean about being able to progress through the room, right? And then what do my actions do, right? So those are both related to one another. The idea being that you combine all that information to say, okay, what might things be like if I do this action? Now, I compare that to my goals, an additional layer here. And now I say, okay, which action is most aligned with my goals? I'll have to simulate several possible actions, of course. This flowchart just shows a simple single case, but over time I will then compare lots of possible actions and then decide what action I should do right now. And then I pass that action on, just like, finally, similar to the reflex model, right? I actually do have to produce some kind of behavior. This might sound familiar in terms of Shaky the robot, if we recall. Shaky perceives the world, it deduces possible action plans, and then it executes them. It's able to take in information, compare possibilities, do its logical deduction, and then execute its planned actions. Similar is Deep Blue. Now, Deep Blue, its search is brute force. You remember Deep Blue? It's the computer designed to play chess, right? And it beat certain grand champions back in the day because it's hardwired with millions and millions of wires to help predict decisions, right? But Deep Blue only used brute force, but it was still comparing possible options using a goal. It wanted to get as close as possible to a win state in chess. So it was still a goal-based action, even though it was using a sort of dumber, harder strategy to figure it out. And I say dumb not just as an aspersion. It is a less intelligent the way to process the world. It is a less intelligent way to try and compare things. It just compares everything, right? If you remember the traveling salesman problem we tried out, that, you don't want to do every possible combination. It's too many. It's a waste. That ain't very smart, right? So, okay, goal-based agents. Goal-based agents can make sophisticated decisions. They actually can decide things, not just like reflexes where they just act automatically, but they can make actual decisions in the world. And they can handle more complex scenarios. So, as the world gets more complicated, we need better ways of navigating all the possible options, right? So a goal-based agent is capable of that. And then, the reason it's able to do that is it has this searching capability, this predicting capability. It has these two options for trying to figure out what to do in the world. Those are related, actually. So searching possible spaces, but also predicting those spaces in the first place, right? But the issue with this kind of agent, because we've seen some other kinds of agents by now, and we are other kinds of agents ourselves, this kind of agent is static. There's no learning going on inside of a simple, relatively simple goal-based agent. And we've talked about some ways that neural networks can learn. We talked about some ways that even physical symbol systems could combine new information to learn, right? So let's talk about learning agents, yet another layer of complexity on our simple agents. So on top of the decision making, learning agents are able to understand error in the world. So compares its predictions about what will happen to actual outcomes. And it also has this ability to experiment. It's the idea that it tries new solutions that don't exist in its search trees by creating the possibility of, okay, so I don't know what happens when I do this. Let's find out. So this leads to a system that perceives, behaves, and learns. That's pretty cool. And decides, right, of course. So let's look at this. It's a little bit different layout this time, but percepts come in, as always, from the environment on the right. They hit the sensors. And then this being a supervised learning type scenario, there's also sort of pre-baked in performance standards, which is I want to minimize my error. So the critic is what will assess whether or not there was error in our decision making and our predictions, right? So, okay, let's stick to this to right for a moment. The percepts come in, sensors take in that information, and then there's the performance element, which is very similar to what we saw in the goal-based behavior, right? The goal-based agent, which then will somehow select some option, and then the effectors will take that action, right? So that little loop aside, we also need the ability to learn. So other information we take in from the world, not just things relevant to our task, but things relevant to our past behaviors, those get passed to the critic. The critic compares it to the performance standard, and then the critic will give feedback to the learning element. The learning element will, interact with the performance element to change what it knows about the world, right? it takes it gives back knowledge and it takes in possible changes. And there's also the idea that we might need to create new possible problems to learn about the world around us in things we didn't know yet, right? So that problem generator can give the performance element experiments to try. There's a lot going on here, but the idea is that this is yet another layer that we can give to an agent to make it more powerful in understanding its world and being able to navigate that world. So this is yet another layer of complexity. Let's look at an example. We can talk about the even something as simple as the backpropagation network, right? The multi-layer networks that use backprop. It will take in inputs and examples. The examples will help train its basic knowledge, and then as it makes predictions about those examples, it will update itself. The critic, quote critic in this case, is just the way that backprop works, right? So it tries to predict an outcome, and then the error signal will be given to the system and go back. Now this is an extremely limited example. We can talk about a different example. Google might be a decent example of a learning architecture, a learning agent. You might not think of it that way, but let's look at it. Google perceives your query, right? Your search query. It searches for answers and tries to give you the best option, right? And so that's it internally saying, okay, this is what was given to me. I need to search these, hundreds or thousands of pages on some index to figure out, what's the closest? What might this person want? Then here's where the learning part comes in. That's the basic goal-oriented agent. On top of that, its quote critic is also looking for, what did you actually click? What Google gives back to you is its predictions about what you might want in ranked order. And if I click something that's not the first click, that's a little bit of error. That's a little bit of updating performance standard. So now it can create this system that reorders your searches and learns your desires based on your behavior. What you give to Google allows it to train itself to better understand what you want. Now, there are benefits and drawbacks to that kind of thing happening in our search engines. Filter bubbles are huge. Look into them if you're not aware of filter bubbles. I'll take a brief aside on that. That's very important. The idea is that as these systems get more and more trained to what we want, they start just giving us what we want, right? So this agent has run wild on, using its learning capabilities, but it kind of puts you in a world that is a bit isolated from others, slightly, in subtle ways. Be aware of that. That's a modern challenge that we're only kind of coming to grips with these days. So keep it in mind. But know that Google is a learning agent. It's not just a goal-based agent trying to deliver you something. It is a learning agent. So learning agents add this extra layer of adaptability to the system. It makes it so that any agent that has a learning capability can adapt to changes in the world, not just automatically dispense things that it already has been trained for, or built for. So information comes in from the environment, and it affects how we change the world, and it also affects how the system changes itself. So that's our 3 levels of complexity, of agent complexity. Simple reflex, goal-based, and learning. And each one exhibits different capabilities. So things that we might expect something to be able to do in the real world. One takes basic input and output, one adds decision-making, and one adds these adaptive learning, evolving, developing processes to it. What might we think of the Chinese room viewed through this lens? In different takes on the Chinese room, of course, it might be a little bit different. In the very first take that the Chinese room was designed to approximate was, I would say it's probably a reflex agent. It has no decision making going on. It just spits out. You read the rule you need and then you spit it out. Now, of course, the other arguments started to come in and add new layers. Say, what if this system can learn? What if this system can make decisions, right? Because ultimately, there's no such thing as a Chinese room, but it's a thought experiment. So it's an interesting take. You can see how it sort of scales around, though. It slips around. It could be very, very reflex if we conceive of it one way, or we can add these other capabilities, and the question changes a bit about, hey, how intelligent is this system? Let's also talk about elevators again. So, I don't know if you know this, but elevators in large buildings have a really daunting task. They classically, historically, elevators in large buildings have a daunting task. They have so many floors. Imagine maybe a skyscraper, sure. And every floor has a different company renting it or whatever. And you have lots of people who all need to go to lunch somewhere between 11 and 2, right? They're all trying to get up and down this elevator. If we just let the elevator run on its own in a reflexive way, it would be chaos. No one could ever get an elevator when it was needed. Now, if we imbue it with some goals and some ability to reason over possible states, that's pretty good. That's pretty great, actually. That means we can program it to say, hey, I got 3 calls above me and 4 below me, but these 2 are closer together. Based on some contextual information in the environment, it can compute what's my most efficient route and do it. Whereas the reflexive version of an elevator would just say, I've received a ding, I will go to that floor, right? That's not good when hundreds of people need to get out of this building over a very sort of a compressed time span. No, so what actually is happening is these elevators are given a learning system. They have a learning subsystem to say, hey, based on what is actually happening in your building, which might change month to month, businesses move in and out of these places and things alter, and maybe something like a pandemic comes and changes what the rush hour is and how many people are in the building, that kind of thing. So they actually do have a complex learning system installed in them to help them better predict, hey, where should I wait when no one's around? Where should I wait when 11 a.m. started, right? It's able to learn from the actual environment around it, right? So that makes it that robust, right? And even elevators can be learning agents. But this leads us to a question. Which one of these is a mind? And the answer is none of them. They do some really impressive things. We've seen how adversarial neural networks can make some pretty wild imagery, very realistic stuff, and how we can make robust problem solvers and deciders and such like that. But these aren't a mind yet. These don't represent what an organism has to use to survive in the world entirely. The elevator does a good job, but it's still not necessarily a fully fledged mind. So minds are complex and they are robust. They have quite a lot of general problem solving abilities that most of these other systems wouldn't yet be considered to have. I can throw any new problem at you and you will eventually find some solution for it. Usually, depending on how esoteric the problem is, right? I'm not going to give you diffie-Q and say, just figure it out, right? But, we can solve all kinds of things. We solve novel problems every single day of our lives. So the mind is really, really a powerful thing, and it's on this continuum somewhere, but it's just further along. So let's talk about how we can conceive of what a mind is up to. Let's talk about modularity of mind. You can, in the way that you conceive of a mind, you can break it up into distinct modules. If we think back to Sherdlu, for example, or any of the models we've just looked at, but modules are the distinct components that do different kinds of jobs, but interact with one another. They are able to, like Sherdlu had different distinct submodules that would help it chop up words, figure out the lexical features of a word, but also figure out the syntax, right? Like a different subsystem would take care of like solving the syntax rules. And the idea is that these different modules share information, but they do different things. So a memory module might be able to provide all kinds of pieces of information to everything else, but it has its own internal functioning to be able to do that. Whereas a learning module would be able to update memory and knowledge, but it doesn't necessarily access knowledge on its own, right? Vision module can give information to memory. It can say, hey, we've just seen a cat, but it can't, it doesn't access memory on its own, right? They are all subsystems that can interact together. Now, there's an interesting tidbit here. Is this just phrenology? If you've heard of phrenology, that's Franz Gall's theory that you can measure the skull to determine someone's personality. That's absolute bullpucky. That is not a thing that you can do. That's not how skulls work. That's not how brains work. That's not how personality works. That's how nothing works. It was an attempt to make sense of the world because they knew that the mind lived in the head, in the skull, in the brain, but they weren't sure what the heck else was going on. But the thing about bad science is that it's typically an attempt at good science, and it's based on some fundamental ideas that aren't necessarily bad. So what Gall was getting at was this idea of faculty-based psychology, the idea that I have different sub-abilities in my brain that I might be able to use in different ways. And they might be more and less developed. They might be, in an individual person, they might be, broader. Some people may have different faculties than others. But in general, there are these different sub-abilities, these different information processing faculties that we have that we can make use of. So there are two takes on these faculties. Horizontal faculties is the idea of there are just a whole lot of general purpose processes distributed throughout the mind. Memory and attention and perception, right? And they can all be studied distinctly, but they all definitely interact with one another. Whereas there's also the idea of more hierarchical version of this called vertical faculties, where there are lots of specific smaller scale faculties organized under a general faculty. General problem solver. So several fixed processors that do hyper-specialized jobs and one great big central processor that coordinates everything else. So the distinction between these two is the idea that horizontal faculties are we don't need to specify exactly how memory works, we just know that it does and it exists. Just like we don't need to specify exactly how perception works. It might be a little bit loose. It might be able to evolve and change and do various kinds of jobs that we don't all know about. But vertical faculties is the attempt to give a little bit more structure and saying, okay, there must be fixed processors in the mind somewhere, right? Neurons that are trained up to a very specific job, and then maybe then there is a more general processor. This is trying to get us into a space where we can more carefully pull apart how exactly the lower level faculties might affect a higher level one. That doesn't mean that the horizontal faculties are right out. In fact, some still believe that that's the better overall approach, that central processing is not necessarily the best way to categorize this. But it's useful for thinking about the mind, because again, these are all very complex interactions within our mental systems that we need to figure out. So that's where these vertical faculties come in to say, hey, let's try to put a structure on here and see what it looks like. Jerry Fodor is a big fan of these vertical faculties. He's a philosopher of mind, brought a lot of computer technology approaches to the study of the mind. And his points are this: there's plenty of evidence that we have very specialized processing somewhere in the brain. there are ways that we've pulled apart how exact little subclusters of neurons do things, right? And more complex skills like insight, we can just leave a little bit more on the table of central processing and say, hey, that's a big, more complex thing. Maybe it's too complex. Let's focus on the smaller things that we can really nail. So, in this view, central processing handles all the really complicated stuff, but lower tiered things exist, like perceiving color, or analyzing shape. Like we've talked quite a lot about the idea of neurons being able to detect edges, right? And then scale a layer up. This is in the multi-layer modeling approach to vision. Scaling up to edges might become surfaces. Surfaces might become 3D proto-objects, right? And then you keep scaling up all the way until you get to something like a very fixed face recognizer, which we have. The fusiform facial area in your brain is a region that will typically light up brightly for faces and not for other things. Now, it doesn't mean it's perfect. It also lights up brightly for houses. Houses kind of look like faces, with the door being a mouth and the windows being eyes. Again, the idea being that little submodule, it ain't perfect, but it has a function, it has a job to do. And I would say that it's actually doing a good job when it sees a house as a face, because then it says, hey, I think that might be a face. And then other systems further up the chain, up in the central processing, can help deliberate, no, idiot, that's not a face, that's a house. But the face recognizer was doing its job. So let's look at different low-level module features. This is Fodor's approach to saying, okay, what can we say must be the features of any low-level module that we want to propose exists, right? So this is sort of like he's defining the outline of the whole thing. So a low-level module, a very, very specific, hyper-specific module, needs to be domain-specific. So it needs to process one kind of information into another and not be general. We can't just give it images or sounds or or thoughts or information from a different place. It needs to be very specific, right? So it may change a visual pattern into a different visual pattern, but it may also change an auditory pattern into a sort of a semantic lookup, right? So the word cat turns into some sort of understanding of cat, right? So somewhere along the chain, he would say that there is a domain-specific module handling that transformation. He also says they have to be encapsulated. So they have to do the job on their own. They take an input and they spit out an output, right? That can lead to a more complex place, but every individual module has to be isolated for us to be able to make sense of it, is the point. It also has to be mandatory, so the processing must be automatic. I can't stop this processing from happening. It's kind of like when you're deliberating over, what should I do today? Where should I go? Not that much of a difference these days, but this has to be an unshakable thing. It has to be an automatic process that your system handles. It has to be pretty fast. It can't be a long-term process. It has to be at the level of, the time order of, simple, very, very minuscule interactions at the neural speed, not at the higher level deliberation speed. Also, he would say that the module needs to be fixed. It needs to not have a whole lot of variety. It shouldn't be learning a whole lot in a given moment. It needs to be sort of doing the same thing every time. And it also needs to fail in expected ways. Okay. Take a brief aside and think about this in terms of a car, right? A car can do all kinds of things. It mostly does exactly what we tell it, but the point is that it can drive over different kinds of terrain. It can drive over, it can drive fast or slow. It can do all these different things. But every subcomponent of the car has a similar set of these ideas, right? The way the fuel injector works, right? It is domain specific. It takes fuel and spits out fuel, right? It doesn't allow outside information to change how it works. It it has to work. It works no matter what is happening else in the car. Even if you blow a gasket, the fuel injector still tries to work. It does it fast, not at the order of the whole car as like where are we going, how long is it going to take, but on the order of half seconds, milliseconds, right? It is pumping fuel into the injector. And then it's the same. It doesn't change, and it breaks down in the same way every time, right? I've never had a fuel injector break down, but I imagine there are gaskets and flanges and mechanical parts and such that break down in a very specific and predictable way. So, this isn't to say that the mind is a car, but it's to say, the reason Fodor goes so far with this to make sure it's clear is the idea that neurons behave predictably, so small groups of neurons probably behave predictably as well. And there must be some way to define how those little groups work, especially the ones that are common to everyone, right? Some of our machinery is unique to us, I would say, but some of it is identical. And let's look at some evidence of that. Here we have the Shepherd illusion. In the Shepherd illusion, there are 3 different boxes presented. A, B, and C. A is sort of a flat, squat box. B is tough to tell exactly, but it's sort of a similar sort of box. Maybe a little bit longer on one dimension. But C definitely looks like a long, skinny box. And here's the oddity here. The lines on these boxes are all the same. When we perceive them, we do this automated processing to turn them into 3D shapes in our minds. And even though I've highlighted these, it's still tough to force your brain to say, oh yeah, C, the left side of C is the same length as the front of A. It doesn't jibe. We don't see it. We can't see it because it doesn't make any sense. Because we have an automatic processing system that takes these things and parses them into 3D objects. So even though you know better, even though I can show you that these are the exact same length, in fact, do it yourself, compare it on your screen, they're the same. That's the funky thing here. So this is showing that even when we know better, there is some step that we just can't stop from happening in the processing. This also comes up in something called brood parasitism. So, more evidence for these very low-level modules. You may have heard of this before. So, the herring gull gives food to the invasive bird chick, despite all evidence pointing to this being a different species, because the herring gull has a lot of baked-in automatic processes that trigger these instinctual behaviors. Like, I'm going to go find bugs for this peeping bird. I mean, look at how large this chick is compared to the herring gull. The herring gull is very small. This chick is enormous. But the herring gull still feeds it. So, it's the same basic stimuli, a peeping chick, mouth open, hungry, and it's the same, same general form, and the whole species does it, even though this species is generally vulnerable. They can see that this is perhaps not their own chick. It's not like birds are totally, completely idiotic in that sense, but they can't stop themselves from this behavior. It is so ingrained in their system, it is so automatic that they can't unlearn it. Not every bird is like this. I mean, crows show an incredible social intelligence, but some birds didn't need that, and it made them vulnerable to this kind of poaching, this kind of brood parasitism. So, also, cool trick by the mom of this chick is, hey, you raised this. It's wild. So, it doesn't have to be just the low-level faculties or the horizontal faculties, right? Fodor makes a strong case for the idea that there are very, very small individual processes going on in the brain. But there may be middle grounds where the general faculties take over again. So the idea of perception is broken into very, very, very small subcomponents, but it also contributes to a general reasoner somewhere, right? None of that is clear so far. So, there might be lots of lower level processes that move things up and down. So, to summarize this, we've gotten into the discussion of how exactly our minds laid out, what kinds of processing structures exist, not just what's possible, not just what might an individual structure look like we've looked at quite often, but how do these things exist for us, for biological entities, for humans, for dogs, for sea mollusks, right? What does a mind look like, and how does it differ? And so we've seen a sort of a gradient for how different architectures would need to be to enable certain capabilities, right? And we've also added this concept of the modularity of mind, that we can break up the mind into different sub areas, right? If I take a little chunk of neural material, I should be able to figure out how it works. Don't worry, that's not typically how we do it. We don't just take chunks of brain and say, "Hey, do math," So next, we will cover a bit more about how the mind is laid out, and some interesting theories, some evolutionary theories of how that came to be. So, all right, that's it for now. Take care.